Okay, this is AQA, A-Level Physics, 2024, Paper 3A, that's Practical Skills. As per usual, can't show the paper on screen because they're very much not chill about papers appearing on YouTube, unlike OCR and Edexcel. So links to the paper and the mark scheme are in the description. Question 1, we have a micrometer. Oh, what do you know? They call it the ratchet after all. State the resolution. Okay, so we can see that on the main scale, we have a line every 0.5 millimeter. So that's that. And so that means every time the thimble, barrel, whatever, it turns, it does a whole revolution, that's 0.5 millimeter. And so therefore we can see we have lines for every 100th of a millimeter, 0.01 millimeters. So that's our answer. And we know it has to be that because if every rotation is 0.5 millimeters and it's split into 50, then therefore that's going to be the resolution, 0.01 mil. What is the reading on the micrometer? That's nice and easy. We can see that on the main scale, we have gone past, what's that, 6.5 millimeters plus something else. And so we can see that it's between 20 and 25 hundredths of a millimeter. So that's going to be it looks like 22, doesn't it? So 0.22 millimeters. So therefore that's 6.72 mil. And of course, that's supposed to be 1.1, 1.2. Sorry, my bad. 1.3. Wire X is placed. State and explain how the gap is closed just before taking. Okay, so before touching, we use ratchet to turn, which will slip once touching. This ensures wire is not compressed, which would lead, to incorrect measurements. Cool. 1.4, we have the circuit, and what are we doing with it? 2 terminals are used to mount X on ruler. So we have this 1.2 ohm resistor there, and then we have the voltmeter across there, and then we have a switch, naturally, battery, and we have our wire. Okay, what are we being asked? The voltmeter reading is, well, let's say that's 0.931 volts. Okay, and then it's opened, and are we told what the, okay, so we're told that, okay, so nothing's changed, right, so it's just a potential divider. It's just that we don't have 2 PDs at the same time, we're just moving the PD, they're just trying to confuse us. So it's a potential divider, so therefore we can say, I'm going to say V2 over V1 equals R2 over R1, the ratios are the same. And so we're looking for this, so actually we don't need it in volts actually because it's just ratios. So therefore let's say that R2, just moving R1 over the other side. So that's going to be, what was it for the wire? 397 divided by 931 times by 1.2. We know this works because the current is going to be the same because nothing has changed in the circuit. And sure enough, we get 0.51. How many sig figs should we go to? Well, we only went to 2 sig figs with the resistor. We've seen that anyway, so let's go to 2 sig figs here then. There we go. 1.5, we now have a graph of resistance against length, and we're going to have a line of best fit. Determine the resistance per meter of X. Nice and easy, isn't it? Because we know that if we do R divided by L, the unit of that is going to be ohms per meter. And so that's equal to the gradient. Don't forget to, when you draw your line of best fit, to make sure the same in number of points above and below. And then also when you calculate your gradient, make sure that you're saying where you take it from, make it nice and big. It needs to be at least half the height and width of the data points. We get a gradient of around 1.66 ohms per meter. Nice paper so far. Nicer than paper 2, that's for sure. But there's always time. 1.6, which one of these wires is wire X? So we don't have the diameter for our wire X at the minute, do we? But we are told that it's one of the diameters in the table there. Okay, so let's crack out our resistivity equations. So rho is equal to RA over L. So that's equal to R times pi d squared over 4 divided by L, or in other words, pi d squared R over 4L. Okay, so we could find out the resistivity for all of these wires. Is it worth it, or is there a shortcut? Let's put it this way. We can see that, well, we have R over L in our equation there. And so that means that d squared times r over L, because pi and 4 are constants and the resistivity is constant if we're talking about the same material. And so actually that means that we can say that if D is the same for both wire in table and X, hang on a minute, no, it's easier than this. We have our R over L, and that's equal to 1.66. And the only one that's vaguely close is nichrome at 0.93 millimeters. That's the only one that's even remotely close to 1.66. They've been nice because they've kept all the other numbers apart. They've given us nice metals there. So we're going to assume that it's nichrome. It says that the diameter is the same. So are we going, okay, so we're going to have to use D equals 9.3 times 10 to the minus 4 meters. Okay, and we just want to find the resistivity. So resistivity, like we saw, is RA over L. So that was so that was our gradient of, well, we're going to use their value, I think, but they've given us R over L, times by the cross-section area, so that's pi times 9.3 times 10 to the minus 4 squared, and that's divided by 4. So popping all of that in, we end up with 1.08 times 10 to the minus 6, and the unit for resistivity, of course, is ohm meters, not ohms per meter. Not a nice question, though, to be honest. It's a bit difficult to figure out what they're getting at. There's lots of data there. I don't know. Not a fan of that. 1.7, student adds error bars. She estimates that each value of R has a percentage uncertainty. Oh, great. Okay, so R is plus or minus 6%. L is plus or minus 5 mil. Compare her error bars for the point at L equals 200. Okay, this is a weird question. So if we're talking about a graph of R against L, which is what we have, and we have our points, then all the error bars for L are going to be the same. They're all going to be 5 mil. So error bars for L are all same length, size. Whereas the higher we go with our resistance, the bigger the absolute uncertainty is going to be. So like that. There we go. With larger R's, absolute uncertainty is greater. Therefore, error bars taller, let's say. Is that it? Is that all we have to say? Marcin says they want us to actually do some quantitative analysis. So, you know, actually put a number in. That's so ridiculous. So, have a look at the top point. So, let's compare then. So, e.g., R equals 0.35 plus or minus. And so, what's 6% of 0.35? 0.35 times 0.06. And that's 0.021, but you know that you can't give uncertainties to a greater accuracy than the value, so we just have to round it to 0.02 ohms. And then R at the top is 0. Are we going to read in between the line? Ooh, I don't think so. I'd rather not. Some people say you can. I say no. Or do I? Yeah. It's a difficult one, actually, because it would be the lines are going up in 0.5s, 0.005s to be precise, up the y-axis. I mean, I don't see anything wrong with going to half of that again. So it would be 6, 5, 5 if it was to the next line, but it's going to be that, plus or minus. Have I got that right? Oh, I don't know. Correct me if I'm wrong. It's a dumb question anyway. So there's going to be 0.039, so we're just going to say 4. So therefore the uncertainty has essentially doubled at the top. Our scheme goes into all sorts of nonsense about like a fifth and I don't know. 1.8, how can the error bars be used to determine the uncertainty in the gradient of a linear graph? There's two ways you can do it. Either you can do the line of best fit and line of worst fit and then do the difference between them. Better way of doing it is drawing two lines of worst fit, i.e. max and min gradient that still pass through every error bar. And then we say uncertainty in gradient is half the range between the two values. Okay, moving on. 2.1, we have an ohm meter with AQA on an LDR. The ohm meter always displays a 4-digit reading of R, but I'm assuming that the dot can change, yeah. And can be set to different ranges. Okay, maximum reading display. Okay, explain why the reading displayed in figure 6 shows that the ohm meter is set to range C. Because because the dot is in the middle, the decimal point. We can say no other sensitivity has decimal points after second sig fig. If that's not allowed as the answer, I'm going to flip my lid. Yeah, or you could say it gives it to 2 decimal places. 2.2, EV is a measure of the intensity of the light. SI unit is lux. Resistance of, oh my days. So log of R, forget about the unit that they've put in there, we don't really need that. Minus 0.772 log, I'm just going to call that, let's call that EV, plus 5.09. Show that EV for the arrangement shown in figure 6 is about 130 lux. Okay, so we have, well, we want EV, so therefore we have to do some rearranging and delogging and all that jazz, don't we? It is log, so base 10, so that's fine. So I'm going to say I'm going to take away, so we're going to take away that from there first of all. So log our takeaway, actually we can say plus 0.772 log of EV is equal to 5.09, sorry. And knowing our log identities, we have to deal with this first. So we can say that this is the same as log R is plus log EV to the power of 0.772. You must know your log identities, guys. That's that. And then we use our other log identity, and that is you add up logs. It's the same thing as multiplying. So therefore we can say REV 0.000, and that's equal to 5.09. And now we're ready to delog. So we're going to say that delog on the left-hand side, we just end up with this. And then that's equal to 10 to the power of 5.09. And then all we want to do is put that over the other side. And then we can say that EV is equal to the 0.772th root of 10 to the 5.09 divided by R. And what is R? That's, well, it is kiloohms. I'm going to say 2,840. Oof, let's give that a go. I'm going to do the bit in the middle first. So 10 to the power 5.09 divided by 2,840. And then we're going to 0.772 square root, not square root, just 0.772th thingy of that. And sure enough, thank goodness, we end up with 132 ohms lux. Not an easy question. This bit might have caught you out, knowing how to do the 0.772th. It's not often that we have a root to a random power like this. I'm going to write my lux with a curly L to make it clear. There we go. 2.3, we have a graph of EV against X. Okay, it looks like decay. Is it going to be exponential? Let's find out. Is that where we're going to go? What are we going to do? It could be, oh no, it's inversely proportional, right? Okay. It's inversely proportional to x squared, so inverse square relationship. Describe a method to show that figure 7 confirms this relationship. You don't have to confirm many calculations. We know that if things are inversely proportional, we can say that EV times x squared is equal to a constant. Therefore, pick 2 points. Therefore, if gives same value for multiple points, relationship is true. Easy. 2.4, deduce the value of x when, so x is equal to question mark when EV is equal to 130 lux. So I'm guessing that's off the, yes it is, it's off the charts. So all we have to do is say that, like we've got up here, or here rather, we can say that EV1 x1 squared equals EV2 x2 squared. And we're looking for this x2. So therefore we're going to rearrange it. So therefore EV1 over EV2 times by x1 squared is equal to x, I forgot the 2 there, x2 squared. Square rooting the whole thing. Let's write it out again. Therefore, EV1 over EV2 square rooted times by x1 is equal to x2. So that is going to be our, well, let's find our value first of all. Yeah, why not? Let's use the point that's right at the top there. So I'm going to say that that is 210 mil. Don't need to turn it into meters because this is just a ratio game. And that is 1,200 lux. So that is equal to, God, my memory's bad. 210 times by the square root of EV1, so that's 1,200 divided by, what are we looking at? 130. Yeah, why not? And I end up with 638. Okay, R is measured when X is 450 mil. Figure 8 shows the ohm meter. We're going to be asked which one's best, are we? The uncertainty of the reading of the ohm meter is plus 2% of the displayed reading plus or minus 2 in the least significant digit. Ugh. Okay. This means that using range B has the maximum value. Okay. So that means the maximum value is the minimum value, isn't it? Oh, okay. What are we being asked then? Oh man, there's just so much crap to... Okay, right. We're just being asked to find the minimum value. Well, that should be fairly easy, I think. So, so we don't care about that. So, min value for range B. We're just going to have to do the opposite calculation, aren't we? So 0.98. So that's 2% less. And then times that by 1,000. They didn't use brackets. That is bad. That's so bad. That's so bad. That's really bad. Like, we don't do... what do they even call it? Well, we don't even do it. I've forgotten the name. Bidmass, bodmass. We don't even do that in physics. We use brackets like normal people do. That's so dumb. Maths is a language, guys. If you don't use the correct punctuation, you're screwed. Oh, that riles me up. Okay, and so then we're just going to take away 2. Fair enough. And then max value, and then the opposite. So max value for C is equal to, so 1.02 times by 1.68 plus 0.02. Even if you had no idea what you're doing here, they've given you the calculations, so you can infer that it's going to be that. So it's going to be, of course, it can only be to the same number of sig figs. So we're going to say 1,645 ohms for that. And this gives us 1.734 kilo ohms. Oh, no. Why did I write the 4 there? Because it only goes to hundredths of kilo ohms here. Not hundreds, yeah, hundreds of kilo ohms. Tenths of ohms. 10 ohms. That's the last sig fig. Silly me. 2.6, we now have the LDR being used to investigate the transmission of light through glass slides. Okay. R is recorded with different numbers of slides. EV is calculated for each value of R. The position of the lamp on LDR. Okay. Identify 2 other control variables. We should say ambient light / we should carry out in a dark room. It's quite a nice question, this, actually. Well, we said the position of the lamp, but we haven't said anything about the lamp itself. So same power to lamp, or rather we should probably say same voltage supplied to lamp to make sure that it stays at the same brightness. That's nice. 2.7 for the arrangement. Oh, we got another equation. Nice. 400 E. So we've seen a question like this before, actually. You should remember before we even start that this can have no units, so that should help us. Is it going to help us? I don't know. Yeah, n is the number of slides. Mu is a constant, so it's actually just going to have no unit as well. If it's just a number, it's just going to be numbers to the -1. Explain how mu can be determined from a linear graph. Again, we're going to use our log identities. That's nice. It's not often that we use log identities twice in one paper, but that's good. So we're going to say that EV divided by 400 is equal to e to the minus mu n. Natural log in both sides. Don't say ln. That's weird. And then we're going to split up our logs. And so therefore, all we have to do is pop that over the other side. So therefore, this is y equals mx plus c. So we're going to have a graph of log EV against N. We don't really care about the log of the 400. That's just going to be our y-intercept. Maybe it's worth just knowing that. And so therefore we can see that mu is equal to negative gradient. Is it going to be negative gradient? So this is our M. Yeah, that makes sense. 2.8, we found that mu is 9.0 times 10 to the minus 2. Just give us 0.090, man. Deduce the minimum number of slides needed to reduce EV by 50%. Okay, so if it's 50%, then we've got 400. So this has to be 200 because this has to be a half. Is that fair enough? We're going to say that, let's write out the equation again, shall we? So we have the log of EV over 400 is equal to minus mu n. We're looking for n, therefore we're just going to take minus mu over the other side. So therefore n is equal to the log of 0.5. We know that. We didn't even have to write the 200, because if we're talking about reducing it by 50%, we're going to 50%. So it's just a log of 0.5. So this actually just ends up being, if you know, that's the log of a half and the log of 1. So this is the same thing as log of 1. Take away log of 2 because it's log of a half. And so that's over that. And so actually this just ends up being, because that ends up being 0, log of 1 is 0. This just ends up being log, minuses cancel as well. Log of 2 over our mu of 0.09. And it gives us 2 sig figs, I think, 7.7. Oh, so we're talking about the minimum. Right, so if it's minimum, so this is to achieve half. Yeah, so if it was 7, then it wouldn't be half. So therefore it has to be 8. That was basically a question on half-life, really. 3.1, we have a copper rod, conductor, flux density, okay, magnetic fields. Okay, describe a method to show the copper rod is horizontal. Your method must include the use of a meter ruler. So we're just going to measure it in 2 points. So measure height, silly question, of ruler. That's assuming that the table is horizontal. Oh, it is a horizontal bench, of course. At 2 points or multiple points using meter ruler from bench, 0 mark at bench. However, it must be perfectly perpendicular to ensure perpendicular. So always a good thing to have ready to go. To ensure perpendicular, use set squares. Use set square between meter ruler and table, like so. There we go. And then there's the ruler that we're measuring the height of. And we need to do it like there too. Give some actual physics, please. 3.2, we have the rod now with magnets, and okay, so we have our battery there and the rod is there. That means the current is going to the right, so I to the right, and we're told that when the switch is closed, the reading on the balance decreases. Right, so when on, force on magnets is upwards because the mass is decreasing, or the measurement on the balance is decreasing. Therefore, the force on the rod has to be upwards due to Newton's third law. Okay, so force is downwards like that. Just downwards like that. So using Fleming's left-hand rule, we find that B is out of page. We know it has to be one or the other, into or out of page, because you know, the force and the current are on the plane of the page. So therefore, thinking in 3 dimensions, it has to be in or out. But it turns out it is out of the page. And we can draw that like that. 3.3, solid line shows the, so that's M1. And then dashed line is M2. Okay. And what are we being asked then? It's a different scale for both. It can be shown that M is equal to, KBI plus NZ plus Y. What the heck? So Z is a mass. Tell you what, let's say kilograms. Y is a mass of the yoke. And then M is going to be in kilograms as well. Right, it's going to be something to do with G, one would assume, right? Oh, I don't know. Okay, so if that's the case, then all of this has to be kilograms too. So therefore, the unit of kBi, this is how you can write it, is equal to kilograms. And we know that the unit for magnetic field strength, flux density rather, is that, Tesla, and then it's amps. But we're being asked for it in base SI units, so therefore we're going to have to split Tesla into something else as well. We know that F is equal to BIL, so therefore B is F over IL. This should ring a bell. Units of this is newtons per amps per meter. Newtons, again, we can't leave that as it is. And we know that that is to do with mass times acceleration. So that is kilogram meters per second squared. That's MA. And there we go. Look at that. We have M's cancelling. Right. Ooh, this is looking interesting. So therefore, we're going to say that this is the same as kilogram seconds to the -2, amps to the -1, and then times by the amps there. The amps cancel. And then actually, that means that we end up with the units of K being kilograms divided by kilograms times S to the -2. Kilograms cancel. S squared ends up being on top. So actually, it just ends up being S squared. That's our answer. Not an easy question, though. 3.4, determine Y. So we have the two graphs. And so we have the solid line like that. And the dotted line, dashed line, whatever, like that. Okay, let's get the equation again. And figure out what everything is here again, because I wasn't really concentrating last time. So this is the balance reading. K is just a constant. B is flux density, that's fine. N is number of magnets. Z is the mass of each magnet. Right, okay. Mass of each magnet. And then Y is the mass of the yoke. Okay. So this is going to be our Y-intercept. Are we going to end up with simultaneous equations? Maybe. So yeah, this is Y equals mx plus c. All of that is our c. So that means that KB is our gradient. So that's going to be our gradient. Let's write down our first. Let's find out our M1 gradient. No. What am I talking about? All we're looking for is Y. So actually we don't care about the gradient at all because we've got our Y-intercepts. I knew there was something I was missing there. Cool. So I'm going to say YM1 is equal to, what's that? 100 and, what are they going up in? What the heck? So it's 0.5. So it's 0.25 each. Are you kidding me? So that's 135. Oh my days. So 134. I'm going to have to write this down. 0.75. And so then that's 134.8. And then 134.85. Right. That's what it is for M1. That's equal to kilograms, of course. For M2, it's equal to, I'll tell you what, we don't even need that. Forget that. That's 100 and, I was in a similar place. So 100 and looking at the other scale for M2, that's 182 working backwards. So that's 170, so 181.95, 181.9, 181.85. Sorry guys, I have to do it this way. My simple brain can't cope with these scales for some reason. Cool. So we have our different, it's the same distance below, isn't it? Whoa, why is that? Okay, so this is equal to, for the first one, that's 2 magnets. So N is 2. So 2Z plus Y. And then the second one is 4Z plus Y because it's 4 magnets. Right, so now we have our simultaneous equation. This is not an easy question. So I'm going to make Z the subject here. So I'm going to say 134.85 minus Y is equal to 2Z. I'm going to write my Z's like that, methinks. So therefore divide the whole thing by 2. So let's pop this in there. So that means 181.85 is equal to, well, 2 lots of there. So I'm just multiplying this by 4. So it's just going to be 2 times 134.85 plus, sorry, minus, it's a minus there, isn't it? Whoops. Minus 2y plus y. Whoopsie, I've written that wrong there. Okay, so this just ends up being minus y. So therefore I could go around the houses here, but I can see it's going to be just that 2 times 134.85. Take away 181.85. Not an easy question though. And that gives us 87.85. Are we going to 4 sig figs? Yes, because our readings on the graph have been to, well, 5 sig figs. And, well, n is just a number. So I think that's fine. And that's grams, not kilograms. 3.5 copper rod is positioned incorrectly. Yeah, so it's not between the magnets. Compare the student's graph with the graph of M2 against I in figure 13. Okay, so M2 line the same. Okay, so how would M1 change? So rod is not between magnets, therefore B would be lower. So if that's the case, going back up here, we saw that, well, the y-intercept doesn't depend on B at all, does it? Because B is just in our x, in our gradient there. So we can say that y-intercept not affected as independent of B, because, you know, the y-intercept is when there's no... we can say, though, that gradient is equal to KB, so therefore gradient less steep, shallower. That's it. Okay, that was a nice finish. It's not a 3-mark question if you ask me. Well, there we go. We made it to the end of the 2024 papers, or at least the non-optional module ones, but I am not doing those. So, hope you found it helpful. If you did, please leave a like and a comment, and click on the card to go to the playlist for all of the papers, and I'll see you next time.